All right, so good morning to my colleagues here in the United States, and good evening to our colleagues and friends in India. Welcome to the first seminar in 2021. We had almost a month-long break in the Binghamton University and VIT seminar series, and this is our first one in 2021. So we are delighted to have everyone join us today to attend the first session, which is focused on design and additive manufacturing of dynamically similar artificial wings. Today's seminar will be presented by Dr. Jia Deng, who is an assistant professor of system science and industrial engineering in the Thomas J. Watson College of Engineering and Applied Science at Binghamton University. Dr. Jia Deng joined our department as an assistant professor in 2017, and he earned his bachelor's degree in 2010 from Wuhan University of Technology in Wuhan, China, in the field of process equipment and control engineering. Then in 2013, he received an MS degree in mechatronics engineering from Huazhong University of Science and Technology in Wuhan, China also. In 2017, he received his Ph.D. in industrial engineering from North Carolina State University in Raleigh, North Carolina. His research interests include process innovation and applications of AFM-based nanomanufacturing and additive manufacturing in biomedical domain. So on behalf of Binghamton University and VIT, Dean Vasudevan, our co-host of this seminar, we are delighted to welcome you, Dr. Jia Deng, to this seminar and invite you to start your presentation.
Thank you. Thank you very much for your introduction, Dr. Kansani. And thank you all for your participation. It is great to have this opportunity to present my work, design and additive manufacturing of dynamic similar artificial wings. So today I'm gonna first talk about introduction, and then the dynamic characterization of insect wings, which are real wings, and then I'll talk about design and fabrication of artificial wings. And then I'll do a comparison of the real and artificial wings. And then I'll have a brief conclusion and discussions. So first of all, so currently there are numerous centimeter and millimeter flapping wing micro air vehicles have been designed using insects as inspiration. Such as the pictures at the bottom right. So it shows a Robo Bee. It is a flapping wing micro air vehicle. It is designed by designed and developed by the Harvard University. They spend like 1 or 2 decades to develop this kind of new robots to have for multiple applications. So think about it in a situation that there are like very complex piping networks that used for transporting very important gases or poisonous gases for some chemical or applications. So it is difficult to inspect, but with those kind of robots, if there are some chemical sensors on the top, the tiny flying robots, the micro air vehicles, can fly along the pipings. So you can detect where the gas leaking and the monitoring. And also there are so many other applications for this kind of flapping wing micro air vehicles. So that's why people spend a lot of time, money, and efforts to develop such a kind of micro air vehicles. So as a biological engineered wing flaps, so as you can see the picture, they deform from both aerodynamic and inertial electric forces. So so currently there are challenges. So the challenges is inefficient energetics and unreliable onboard sensing. So usually this kind of flapping air vehicles, they need batteries, but the battery is kind of heavy, and sometimes they use a kind of long wire to wire the energy to it. So the energy efficiency is quite important. But think about the current flying robots, like the commercial airplane we take every single day. And also those drones, they either use static wings or they use rotary-based wings. So those are not actually energy efficient, and it will have some problems. But think about the actual birds, butterflies, right, insects. They all have those wings are flapping because they're biologically efficient, energy efficient. So there are those. So wing is actually one of the challenges to actually reduce the energy consumption for using this flapping wing micro air vehicles. So there are some existing research about the wing static and dynamic characterization. So for example, for a static test, the stiffness is very important. So researchers test about various different kinds of species and different winds. For example, first, the hawkmoth's Manchuka sexa winds, it decreased the flexural rigidity from the wing root to the tip. So because the root always have kind of wider vein structures. And the chord-wise stiffness is an order of magnitude less than the span-wise. So the chord-wise is really stiff than the span because span the wing got to flipping, so that's why. And honeybee, the four wings have different differences between span-wise and chord-wise stiffness, and similarly. And besides the static test and also dynamic tests have already been determined. So researchers try to understand how the wing behaves under time-dependent loading. So for example, the honeybee, again, did not flap at their wing resonance. And also some little added mass could reduce the first natural frequency of the four wings about 30%. So the first natural frequency is actually usually corresponding to the bending. We're gonna talk a little bit about details later on. So because there are so many important function and properties of the wings. So the fabrication of the wings are very important. And the researchers have developed several existing fabrication processes. For example, this one is people using a carbon fiber, okay, as a venation. So those, and also they use a 1.5 micrometers polyester membrane to emulate the membrane on the real vents. So the entire fabrication structure is as follows. So first they use a photolithography, and then they use a real wing structures, vein structures. So the vein structures can be transferred onto a silicon substrate. And then there's a PDMS reverse mode. And then PDMS get a kind of reverse protruding structure. And then there is a reverse casting, and get a vein structure out of a mode. And then the people manually put those carbon fiber as a vein, as a kind of bone of these wing structures. And also finally, they cover a 1.5 micron polyester membrane as a step 8 as a final results. So the real products are shown here in the right top picture. So you can see this is one of the way, and another way is people doing instead of photolithography, they do laser cutting. So using lasers, they cut the similar shapes according to the location of the vein structures, and then also manually put the carbon fiber based materials as a vein structures, and also put a membrane as it to emulate the structure, and finally got the artificial wings. Okay, so you can see at sub figure B, the left side shows the real cicada wing, and the right side shows artificial cicada wings. Okay, so those are some existing wing fabrication processes as a introduction. So for our research, our objective is to design and fabricate biomimic wings that has similar morphological and dynamic properties of the real wings. So morphological means mass and size, means similar weight and similar dimensions. And also the dynamic properties. We're trying to get the wings is have identical the mode shapes, which is natural frequencies and geometric properties, aerodynamic coefficients, etc. So our motivation is because currently, even though there are so many researches that have been done to test out the stiffness, the aerodynamics, and also there are different fabrication methods to fabricate those wings. And there's no existing research talking about has been designed to both isospectral and isomodal with respect to its biological counterpart. So that means if we can get a wing that has very similar morphological and dynamic properties, it will be ideal for future flapping wing micro air vehicles. Okay, and also it will definitely help to further understand the wing structure and dynamics. So so first, in order to achieve our goal and objective, we're trying to what do we do? The first step is dynamic characterization of the insect wings. So for dynamic characterization of insect wings, we select the hawkwall wing, hawkwall moth. So this kind of moth has a wing size about a few centimeters long and 1 or 2 centimeters in width. So you can see this is the left side picture shows a adult moth structure, and underneath is a grid box reference. So each box is 0.5 millimeter by 0.5 millimeter, and the right hand side images shows the camber at the wing base. So there is actually a kind of traces, shows it's not a very flat wing. It has some curvatures at the base as well as at the end. But however, the curvature at the base and at the tip of the wings are not the same. And also you can see if we actually squeeze it into even though it has curvatures, we're trying to know the actual area. So we're trying to squeeze the wing to the flat and make it on the grid paper. It shows the size, and this is the section, the forewings of this hawk moth wing. So those are the real biological wings we use. So we're firstly trying to do the morphological properties and characterization, and also some dynamic characterization. So as we're using the real wings, as you can see, we use A samples to measure the mass, area, span, the max chord. So as you can see, for all those 8 wings, we have the mass about in average mass about 36.6 milligram. And also it has a standard deviation about 3 milligram. So you can see for this kind of wing is very light. So even the paper has the same kind of shape and size, will be heavier than this kind of wing. So this is also one of the challenges we encountered. And also the area is 6.77 centimeters square, and span has like a 4.8, and the max chord has 2.03. So those are the morphological properties. And in the span, as you can see at the bottom image, so the span is kind of a few times more than the chord width. And also notice the right hand side of the image, there's a clumping boundary area. We're gonna show a little bit later on. So as for besides the morphological, which is size and area, etc., weight, so we also do dynamic characterization of the real wings. So the experimental setup is shown at the left side. As we can see, there is a setup of electrodynamic shaker, as you can see, is a very big box. And also there, to drive this, there are some function generator, and also there is a clamp to clamp the wings to fix it, and also there's a accelerometer to get signals back. So the vibrometer laser is trying to get the scan the full area of the wing to get the dynamic characterization. And also the right hand side image shows the wings we designed and fabricated, and shows the clamping area is by a foam structure. So this type of vibration and experiments can do dynamic characterization. So by measuring and characterize all those 8 different real winds, so we get a kind of typical frequency response functions, as you can see at the first image. So the resonant frequency is about between 70 and 80 hertz. So this is the first resonant frequency. And also the second resonant frequency you can see is about kind of more than 100, but less than 150. So it's about 130 something. So the first 2 vibration modes is actually bending and twisting. So as mentioned, so this first resonant frequency corresponding to this kind of a bending vibration modes. So it's more like a bending structure. So you can see the displacement of this vibration mode. And also the second resonant frequency mode shows the vibration is actually a little more twisting. So you can see the displacement of these 2 locations of the 2 vibration modes. So so that is a dynamic characterization. Then we're going to talk about based on the characterization and also some measurements, we do our designs and fabrication of artificial wings. So because the wing is kind of has a lot of variance and is very special, and the size is looking at here, this is one of the reference we have. So first we kind of squeeze and flat this wing structure onto a grid box. And this is one of the design references, which gives us the contour and the shape of the outside. And also it is very important to know the inside, the vein structures. As an introduction, I mentioned many people using carbon fibers, manually put carbon fibers to the vein structures, because those veins are like the bones of or skeleton of the human beings. So it's very important to support the entire structure. So we got to know where the bones are, where the veins are, so you can see where the shapes are. So we're trying to mimic. And besides, another important information is about the weight. So so we try to cut this real wings into pieces, actually more than 20 pieces. So cut into small pieces and weight, and then form a mass distribution map. So it shows like it is very clear at the root area. This area is connecting to the body of the hawk moth, and it's very heavy and more heavier than the tip area. So those 3, the outside contour, the vein structure, and weight distribution, are our references for design. So our design actually evolved from different versions, and this is a final version of design. And what we do is we design a wing, and then ship it to my collaborator, and then do a measurement, and then if it's good or not, and come back, get some revisions. And even based on these 3 references, we did various of designs. So this is a final design, came out reasonable. So as you can see, the vein structures, we are following the similar structure of the veins. And you can see the structures over here. And also because of the weight mass distribution is heavier here. So we kind of design 3 different layers of, you can see there's a base, has a base structure, and also trying to add some more weight towards the root. So we designed 3 layers here. And finally, because of the mass requirement, the weight requirement. So, I just mentioned it's about 36 milligram in average. Of course, there are some 33, there are some 41s, there are some variations, but the average is 30 something. So we design trying to be as close as possible. And also we cover the membrane. This is 10 micron thickness to cover on the top to see to emulate the membrane of the actual those kind of nano. Actually, those are nano scales. Okay, but it is really difficult to actually mimic those nanoscales. When you touch those tiny wings, it will have a lot of kind of powder-like shape fall off. Those are the beauty of natures, but it cannot easily do that. So we can only do is the membrane, 10 microns, and to emulate the mass. And of course, the contour is the same as contour of these, the size. So based on the design, we came up with a fabrication process workflow. We developed start by doing the 3D printing, because at the very beginning, our design is to be compatible with a FFF printer or FDM printer. So at the very beginning, we designed 3 layers is towards the using of the 3D printing. And then after print those design structures, we cover the wing, the kind of flat 3-layer vein structure with a membrane, 10 micron. And then because there are some curvatures, as I shown in the morphology and dynamic characterization, there are some curvatures here, and also a little bit of curvatures here, but it's not all the same. So we're trying to mimic the curvatures also to be dynamically similar. That's why we also design and 3D printed a mold that can change the curvature of the flat wings. So this mold is designed and printed out using a 3D printer. So we design an inner structure like underneath the mold to blow some hot air. So the hot air is going to warm up the mold and then transfer the heat to the wing. When we put a wing here, and it's going to make it soft, and apply the force, and it's going to and we get rid of the heat. It's going to permanently change the shape, because this is a PLA. We use the PLA as a material, is a thermoplastic. So this is the final wing of the artificial wing, looking like this. It's kind of curvature, and from here, and different curvature here. So it's gonna emulate the. So we print and thermal molded a lot of the wings. You can see here for testing and for measurements. Okay, and again, of course, the artificial wing design, and we went out through different iterations. So this is a final one picture of this. So trying to give some insights, like why we're using FDM or FFF as one of the machine or process we select. Where we're not using the stereolithography, or not using the material jetting, or even other selective laser sintering. The reason we do this because we have already tried all of these stereolithography, material jetting. So stereolithography results came out like this. When we first tried, of course, this is one of the earliest version we have. We have a full version, but it's too heavy. So the stereolithography is is one of the 3D printing technique. So you can see there are some edges and also some uneven surfaces here, and it's very heavy and not easy to print, and you usually get some defects because it's very thin. If you want to print those vein structures, even the entire surface is not possible. So we also tried some material jetting. So we use a very advanced is a machine from Stratasys, Connex 500. It's a very expensive machine, but it won't come out very well because the resin actually automatically became its own curvature without any control, because it's very thin and it's even thinner than this SLA printing process, but it's not controllable. But surface finish is good. However, because of those limitations, and we select finally the FDM or FFF. So some intermediate results. First is 100% infill. We can curve it, and first and second bounding frequency are very close, very good. Okay, we came up with dynamically very good. However, because it is very heavy, it is about 3 times more than the wings. So we cannot do this, even though it's not big. So there are some other designs as well. We're trying to get different curvatures, change different shapes, and then the wing structures. It won't be as good as the final design. And also, we also trying to change some of the coverings, the membranes. Some membranes is clear, some membranes not clear. Depends on. We'll also try some of the films. So also, again, similarly, we're also trying to try different designs of the mold, because the mold at the very beginning, the first version of the mold is looking like these. We have the structure to put the like these without any structure, but the final version, because of the variance, you can see without this. For this one, first version, the initial ones, we can put the wings anywhere, right? Anywhere. So they may slip in here when we do the manual the heat molding. It can change location anywhere. That means the curvature will be not even. And also the location, the wings may slip around. Okay, so you can see this is unevenly distributed curvature here. You can see some curvature is large, some wings is sitting on its kind of this long axis chord, but some wings are different. So you can see it's not uniform. And we think about fixing the wings in the 3D printed mode. And then we design another sink, so the wing has to be placed here without any slipping, without any moving. Then finally get the kind of uniform curvatures. So many iterations. And besides the actual design and fabrication, also have some FE model, finite element model of the wings, and analysis using Abacus. So you can see this is a vibration model of our wings looking like this. It looks like the top with vibration bending is about 70 hertz and 120 hertz. Okay, and also the properties using in this model is listed here. So after we do the design and fabrication of the artificial wings, and we finally compare the real and artificial wings to see any differences, and we do some comparison. So the comparison of these between the morphological and dynamic characteristics of the artificial and real wings are here. So as you can see, the mass and the area, span, chord. But as for the mass, the real wings has 36 milligram, and standard deviation is about 3.3 milligram, and our artificial wing is 42 milligram. So it is a few grams more than the real wings we've tried our best trying to reduce the mass. Okay, and this is so far the best we can get. And but the good thing is we achieve a little bit less standard deviation than the nature, right? And the area looking like this, but also a little bit deviations from the real winds, but the variation of our stuff is almost zero variation in terms of the size, okay, area, span, chord, because 3D printing, we're not using manually fix the winds using the carbon fiber like other research is doing. This is also an innovation here. So you can see it's zero deviation comparing with nature, the nature work. So that is the morphological comparison. We also compare the dynamic characteristics. And as we can see, this is the natural frequency, resonant frequency of the bending. So the real winds has about the 70. We have a very similar, very close, 74. And standard deviation, we have a little bit larger, is very close. And the gain is very typically close. And for the, and this is damping ratio. And also the second mode is the twisting. So twisting, we have a little bit difference in terms of the resonant frequency location. 100 is about 16 hertz more than the 95, but it's okay. It's the best we can get so far. And also the gain is a little bit more. Okay, it's a little bit more. And this is damping ratio here. So I'll try to put together the those numbers in the visualization to see where those are. We just mentioned the first bending resonant frequency here is very close, even though the gain is a little bit more than that. And the blue is the real ones. The red is the artificial ones. And you can see the second resonant frequency is also very close, even though there are some 16 hertz difference, but they're still very close. And up and down, but the gain has a relatively large gap. So that this is the final results we can achieve. So this is a comparison of especially average the frequency response functions for the artificial and the real winds. And also based on that, we also did some the mode comparison to see the bending and twisting. So for the artificial ones, the mode, first mode is here. Artificial one you can see is kind of a kind of bending, but towards a little bit of the tip here. Other than all the tip here, this is biological. It's pure, looks like a pure bending like this. We have a little bit towards this side. And also the mode 2 is twisting. We have a similar, very similar twisting mode here. You can see here. So that is going to be the final results. So the conclusion here is we actually innovated a process to fabricate the artificial insect wings that are dynamically similar with respect to their biological wings. So different from conventional fabrication processes, like those photolithography or laser cutting or some other process. So our process use a preliminary, mostly additive manufacturing and combining with some heating molding process. So to inform the design of the artificial wings, we characterize both morphological and dynamic properties of the real wings, and to using the image-based technique and experimental model analysis. And also the artificial and real wings came out very similar morphological parameters, and we have very almost zero, basically zero variance in terms of the length, span stuff. And the first natural frequencies and gain evaluate are pretty similar. However, the second natural frequency gain is a little bit larger than the expected. So the vibration mode shape has similar characteristics. Okay, So even the exact location has a little bit difference. So the discussions we have here is so far is those are the results we got at the best, and we can there are some optimizations or improvements can do to improve the design and manufacturing. First, 3D printing has its own limitations uh, on the size of the vein structures, because you can see because 3D printing has it's using nozzles. The nozzle has a size we're using nozzle size of 0.4. Of course, we can use 0.25, but even though that one still has the limitation, because the natural vein structures are kind of like a uh, very smooth of those, just like natural sticks we see every time. So it's very smooth, very um, kind of it's not the layer by layer, because 3D printing is layer by layer. There are some of discrepancies in terms of the final fabricated results. So it cannot properly follow the very smooth vein structure of the real wings. So because also because the mass constraint, we only allow like 36 milligram, but the best we're trying to achieve the vibration frequency, etc. Or so we can achieve about 40 milligram, and we can only design 3 layers because we use 0.1 millimeter as a layer thickness. Okay, and also of course, high resolution printers and and the nozzle will help to further improve, but those will be kind of a development. So our this idea and the work will be the innovation and the first work to try to design and fabricate the dynamic similar wing structures. Okay. And also another idea about improve the design is based on the simulation. FE simulation can improve the design by the topology optimization, or if we have better 3D printers, FDM 3D printers available. So of course, in the future, as time going, a lot of high resolution in terms of layer thickness, 3D printers are available, and smaller nozzles. I believe in the future there will be more potential to fabricate very identical wing structure using 3D printing. So we're actually very delighted this work has been accepted by International Journal of Microwave Vehicles. And this work is a collaboration between Montana State and the Binghamton University. So my collaborator Mark Jankowski recently got an NSF Career Award about this kind of wing structure work. It's very good news. And also this work is supported by our Binghamton University and at S3IP. So with that, at least some references here, and also thank you very much for all your patience, your attention, participation. Now I'm open to any questions regarding this work. Thank you.
Thank you. Thank you very much, Dr. Jia Deng, for your presentation. At this point, we will open it up for questions. I saw, I think, at least one question in the chat from Noah. In nature's birds or insects, there are nerve ending that connect to the bird's or insect's brain. Is it the same thing in your wings creation?
Yeah, thanks for the question. It's a very good question. So it's about the sensing, and it's also one of the challenges we have currently for the sensing and to actively control the flapping and get the air dynamic feedback. Currently, our design wings is not equipped with this function yet, but this is definitely the future work because currently the small sensors, flexible sensors, have the great potential. It will not add a very significant weight, but it has a bright future. Thanks for your question. It's a very important question.
Thank you. Thank you very much. I don't see any other questions in the chat. So now we can open it up to the audience. If anybody has any questions, please feel free to
there are,
unmute yourself.
Yeah.
I see there.
Yes.
Yeah, there
Oh.
are a few.
Yes. Okay.
Dr.
Can
Jia
I
Deng,
ask a question?
actually,
Yeah. Okay.
Yes.
so let me take this one. So I am Dr. Keyur Joshi from VIT,
Hello.
and
Hello, Dr. Josh.
yes. So my question is, it's a great work, first of all.
Thanks.
But morphological similarity, in terms of morphological similarity, usually, this wings do not have a frame. So they do, have fingers, right? It's not completely framed profile as such. And secondly, these fingers also tend to narrow down as we go towards the end of the wing, right? So the question is, do they make any difference in terms of the frequency characteristics or other dynamic characteristics?
Yeah, thank you for your question. It's very, very important. So yes, we do see the wings as fingers at the end. And at the very beginning, we're just adding the frames to be stabilized. And then we have, then we developed some fingers and haven't tested it yet. So the fingers has a little bit um, uh, dynamic differences over there. So as comparing with the frame, you're talking about the very end of the tip, right? If I understand correctly.
Yes, yes.
Yeah. So yeah, the dynamically there are some differences there. Yes, and you're definitely correct. Yeah.
Because I believe that will give it, in twisting degree of freedom, there will be more flexibility because there is not the frame is not complete; it's just fingers, so they cannot support twisting moment. So, I do expect that twisting frequency would change.
Yeah, yeah, I agree. Yeah, we haven't tested it out yet, so this is our the best thing we can do so far. So the wings again, because of the 3D printing limitation, we cannot get a gradually thinning finger shapes from the root to the tip. Of course, we would like to have some. So because of the limitation of the printing 3D printing the wheel structures, and this is the best we can do is get rid of the frame, not get the gradually thinning tips. But yes, I agree. It's gonna change the dynamics. Thanks for your suggestion.
Thank you
I
very
have
much.
a question. Hello, Professor.
Yes,
I have a question. I'm Raguraman from the Mechatronics group of VIT. This veins, that flexibility morphology, as Professor was telling, that we cannot reproduce it exactly. Now, is it possible? I don't know. It's a very imaginary question that the veins are replaced by small SMA actuators, very small actuators. Those will improve the flexibility and somewhat it will come close to the morphology. Is it possible to have SMA actuators, very small actuators as veins? Difficult to fabricate, but is it possible that that can happen?
I think. So I'm not sure if I fully understand your question. So you think you're using some other technologies to get similar? Yeah, I would say
using actuators. I think the question, right?
Yeah. Using shape memory alloy actuators, they give a lot of flexibility, but it will increase the heaters and all that mechatronics content will increase. But using such actuators, can they bring in more flexibility? Because we are not able to, in the material, we cannot bring in that much like an insect. We cannot reproduce the insect exactly. So will using SMA actuators somewhat improve it? I don't know. That is it possible wherever required?
we're trying to. So those are the you said from the actuation point of view.
Yeah.
So we use the same actuator for both flapping wing and for the real wing and the artificial wings to try to characterize the dynamics first, and then make it similar. Yeah, it's not about a power source. So we can shake it in different the power, amplitude, and also the frequency. You can shake it in different in many different ways, because because the power is not an issue, because the MEMS will definitely be the candidate for kind of miniaturize the wings if possible, and also but the power is currently is not a big issue so far, as my understanding. Yeah, thank you.
Okay.
So, sir, if I can pitch in here, SMA, sir, would be overkill in this particular application, because it has a lot of strain energy density that it can provide, which is not really required for micro aerial vehicle. And another thing is the frequency response. So since SMA are thermal actuators, cooling them is a problem. And so when you have to operate this MAV at very high frequencies, that becomes a challenge.
Okay, I understand. Okay, fine.
And Dr. Jia Deng, there are I think 3 questions in the chat. I don't know if you want me to read them or if you would like to.
Yeah, I can. Okay. So first is, are the 3-layer wings made separately, or they are shown for understanding? Yes, we design intentionally as 3 layers because we use 3D printers, so they can print into layer by layer. Then we design them into 3 layers, and then the printer is fabricating those in 3 layers. So first is the entire layer, and second is, I can show a slide. First is the entire layer, and then with this kind of we're trying to mimic the weight distribution, so it's 3 layers separately. So second question is real biological wings? In real biological wings, the material property should be quite heterogeneous from place to place. Is it possible to realize such heterogeneity in additive manufacturing? Yes, thanks for Dr. Sayama's question. Yes, actually in biological wings, the material property, you can see the mass distribution is different from place to place. 3D printing has the potential to realize this heterogeneity. That's why we design these 3 layers, and to mimic the mass distribution. However, there's also limitations, saying the resolution of the printer can achieve, and also the smallest in the resolution, and also the weight. There's a very specific weight constraint for this wing, because the weight is very, because we need a very light structure, so we cannot make more layers to be more, but it definitely has very great potential to realize heterogeneity, and this is one step we do. And if in the future we get a more high resolution printing capabilities, we can do that. Again, the next question, your analysis is only considered in 2 modes only. Why not higher modes and natural frequency? So yeah, 2 modes is with regard to the bending and twisting, which is 2 major modes for the we need to consider for the flapping and for the flying insects. And another question is ask you about the structure, which you mentioned during the session, that mimicking the insect. How will you encounter challenges in fields of streamline flow, and also the rolling of the wing during action? So in when we design and fabricate the wings, there are challenges in the field of the streamline flow, in kind of in just curviness. We're trying to mimic the curvature. I'm not sure if this is your intention. So in curving, this is we design specifically towards similarly curvature of the wing. So then we're trying to mimic the frequency and curvature as much as possible. That's from the Gaurav. And another Noah's question. In the visual graph, was shown about the spikes in the natural animal flights versus for robotic flights. There were sharp flights differences. Were they low flight according to the bees work, such going from low to flight? Sorry, I'm not sure.
Joe, if you would like to show the slides, then Noah, I think, can maybe.
Yeah, no, which slides are you talking about? Can you unmute yourself?
Okay, can you hear me?
Yes.
All right. There was a graph that you showed with the spikes, like the natural insect versus. Yeah. I think this is no, not this one actually. There were two of them. Yeah, this one. Yes, yes. Okay. When you look at the blue one, you see there is a little bit of going down. So, and then there is a little bit of going up versus there are two hard, like sharp spike, you know.
Yeah.
Now, I think maybe the difference because the brain was, the bee was thinking about going from flower because she needs to do certain work according her to the designation as a working bee, for example.
I got you. Yeah, you worry about that this kind of this mismatch here, right? Yeah.
Yeah, and if there's
why
no,
can,
yeah.
Yeah. I got you. Yeah, because this is not the actual like when the bee is flying from flower. It is the unfortunately the wings are taken out from the moth, and we fix it into a testing equipment. So this is not actual working of nature itself. It's actually working in the lab, and also it is a kind of average of the response function.
So I don't see it being a true when you don't have a brain that control the wings. I mean, you can't get much because I mean, in real, if you just put a camera next to like a beehive and you just be able to actually put a camera, a miniature camera on the bee's head or something to go where she goes. If the camera doesn't even like, hinder her movement, then you're able to see how she works in real. And those are two, like in the red, two spikes, which means, I mean, is the UAV not able to go like on a lower flight for specific jobs like the bee does? Is it only going up in on a certain way? It looks like it's like limited. If it needs to do jobs, certain jobs like even fertilize flowers because we don't have much bees. So we need to be able to give it certain task, and the brain of the bee needs to think about it. The artificial bee, for example, if you use it for agriculture.
Yeah, you're right. That's why we do this. That's why we do the research about the wings. We're trying to get the wings correct. Then in future, maybe we get artificial robots, bees, right?
Yeah.
To transport the, you're definitely right. Transport the powder and get more nature inside, get more kind of biomimic. Yeah, I agree. Yeah.
I mean, we need to do an MRI or some brain scan for the for the bees to understand how it works.
Understand the bees, right? How they control the wings, right? Yeah, nice idea.
Okay, great. Any other questions from anybody? Again, please feel free to unmute yourself and ask.
Can I ask?
Yes, please.
Professor Deng, very interesting. I have two questions. I can ask them one after the other. The first question is about the term additive manufacturing. I'm not sure I understand why the process is called additive manufacturing as opposed to just manufacturing. Is it something to do with the process? Can you please explain?
Yeah. So first of all, so some previously developed the process using the carbon fibers. They manually put those carbon fibers from into the molds, into the laser cut or photolithography. So it is a manual work. It will have a large variation. So you cannot ensure from the first one to the second one they are identical. So basically, 3D printing it can be automatically produced, right? So this is one advantage. And second is in terms, and you can see from the morphological summary, and we have almost zero variance. But if manually put, cannot have this. And secondly, additive manufacturing saves the materials. So we can see if you use laser cutting that I introduced before, the laser cutting will actually waste a lot of materials because what we use only is the vein. If you cut and not all the carbon fibers, the composites, right? Left over is only this kind of tiny. All the stuff are wasted. And if you really need a carbon fiber, 3D printer can also print carbon fiber, and it wastes a lot of material. So that's and also it's quick. You don't need very like a bulky laser cutter or very expensive photolithography, right? So it's also low cost. There are a lot of advantages selecting the additive manufacturing. Thanks for your question. It's very important.
Okay. And then the second question I had is on the shape of the wings. I know birds have an aerofoil design, and that was, I think, what was incorporated into the design of the wings in our jet planes. So do the insects have a similar aerofoil structure? And is that something that will be attempted in future instead of a contour, or maybe the tip of the contour has an aerofoil design? I don't know. Can you please explain the details there?
I think the natural wings or the real wings are kind of beauty of nature's. It has its own natural folio there, and so first of the curvature, and then the scale. So I can show you so you can see the beauty of the wings. It has. So we just focus on mechanical, and there are so many other things we cannot even talk about. For example, the color, the materials of the stuff, and as we mentioned, the wings are covered by scales. If we touch, there's so many powders or scales falling off. So those are the natural foil structures we in boundary ways. So some nanotechnologies, if in future, can be embedded with the membrane, I would say that would be more close to the real wings, because this is actually the nature did. This is my opinion. I'm not sure. It's
okay. Yeah. Thank you.
Thanks for the question.
Thank you, everyone. I think we're almost out of time. Are there maybe one more question before we conclude?
I'm just have a remark. I think it would be interesting to experiment with different bird species or different insects to learn about the differences of their designation, what they do, and perhaps we can use this for the advancement of technology in ways of different designated jobs.
Yeah, thank you. Very good ideas. I think it's would be high potential to in future research. Awesome. Thank you. Yeah, they are.
Okay, excellent. Yeah. Thank you, Noah. Thank you, everybody.
So
Dr. Jia Deng, again, thank you very much for joining us today and for sharing with our colleagues here at Binghamton and at VIT about your research group and your work. We definitely appreciate your contribution.
Thanks for having me.
On behalf of our colleague, Dean Vasudevan, and Binghamton University, we'd like to thank you again for your contribution.
It's my pleasure. Thanks for having me. Thank you all.
And before we conclude, I just want to...
Thank you very much.
Thank you.
Thank you very much. Thank you.
Thank you. Before we conclude, I'd like to inform you that our next seminar is by one of our colleagues from VIT. This will be again a week from today at the same time. And this will be conducted by Dr. Solomon Bobby Silveraj on laser additive manufacturing for patient-specific implants. So we hope that many of you will be able to join us again next week, and we'll be able to share information about the seminar with your colleagues, with your students and other scholars, and look forward to seeing many of you next week. Okay, and with that, again, thank you everyone for joining us today in our first session in 2021, and we look forward to seeing many of you in the future sessions, and enjoy the rest of the day if you are here in the US, and have a wonderful evening if you are in India. Thank you again for joining us.
Thank you.
Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye. Thank you very much. Bye.
Thank you.
Thank you very much. It was enlightening.
Thank you.
Thank you, Noah. Thank you for your question.